Any more people coming in, I'm going to start the session. It's going to be mainly a session on 3D with a lot of participation from Mello company. The first speaker is Ondrej Prochazka from, he's actually the CEO of Mello Technologies. He's going to talk about topographic labels in 3D maps of high terrain. Okay, please.
Thank you so much for the introduction. Can you hear me well? Okay. Good. Well, hot summer evenings are not really the moment when people usually get interested in high terrain, but I'm glad that I can at least see some people interested in this very interesting topic. I'm the acting CEO of Mello Technologies, and basically I'd like to do a very brief introduction of my company. What we do at Mello Tech is we're a software development company in the 3D mapping business. And we develop software, and what our software does is that we do one, computer vision and deep learning driven reality capture, and two, we do three-dimensional data fusion, virtual landscape streaming, and rendering. Basically meaning that we take the data, like photogrammetric city models, DEMs, or the photos, and we send them to all these devices and form factors that you see on the right, including desktop, mobile, and also major GIS systems and even game development engines, which is an interesting topic. Applications of what we do are VR and AR, interactive simulations, and gaming, and of course, geospatial, which is why we're here. And that brings us close to the topic of this talk. The topic of this talk is actually the conceptual problem behind 3D mapping. I'm saying the conceptual problem, but I think that realizing the very existence of that problem is something that's sorely missing from the entire 3D geospatial development today. The term 3D mapping somehow implies that 3D mapping should have something to do with cartography. However, cartography, after all, is the art and science of making maps, but in the way 3D mapping is carried out today by pretty much any company doing it, has nothing to do with cartography, which is a point I will spend some time laboring because I think it's frankly quite astonishing. Cartography defines a map as a diagrammatic representation of an area or a simple depiction emphasizing relationship between elements of space. Now, I have not invented this. I took it from its combined definition from Britannica and Wikipedia, but we say diagrammatic representation of an area. While in 3D mapping, we usually understand a map as orthophotos trapped over DEMs viewed from an arbitrary angle. Now, I personally do not really see much relation between these two approaches, and that's an interesting point and something that we're going to work with. In cartography, a map works with a hierarchy of features, both intellectual and visual, an extremely important concept in cartography in general. Like, the way things are displayed on a map is dictated by that there is a hierarchy in what you see on the map. Some things are more important than others, and the relative importance determines one, whether the feature is going to be displayed, and two, how a collision between two features occupying the same area of the map is going to be resolved. In 3D mapping, a map aims for data visualization or simply for visual realism, hence those pretty pictures. In cartography, a map relies on cartographic principles, which have evolved in 4,300 years. And in 3D mapping, a map usually relies on applied computer graphics, which is a fairly fresh field, evolving in about 50 recent years. So, pointing out these differences, we should not be surprised that where cartography is going to give you something like this, 3D mapping is going to give you something like this, or even this. Now, all this is generally useful and interesting, but I believe that we should try to look at the problem of 3D mapping cartographically, which brings us to the real goal in this talk, which is to create a free and open source software-based map application, which is going to leverage on the benefits of 3D, meaning it's going to be visually realistic, it's going to offer us all those arbitrary angles, while it's going to stay true to cartographic principles. Now, the case study that we're going to use is a global high-terrain 3D map with VDS, which is our flagship open source product, available to anyone. And the inspiration that we take here are these information boards that you can find many places where high terrain is, you know, like these depictions, panoramic depictions, which show you the surrounding peaks with their labels so that you can orient yourself in high terrain. Here's another American example. And the ingredients that we're going to use in terms of technology is we will need a major distribution Linux server, and of course, the VTS 3D geospatial software stack, which we're going to use quite extensively, from the backend streaming servers, namely MapRoxy and VTSD, to the data fusion command line utility VTS, and also the JavaScript rendering library, in this case, VTS browser JS. There's other rendering libraries apart from JavaScript, but this is what we're going to stick to in this case study. In terms of data, we're going to use the global Sentinel-2 cloudless mosaic, which has been provided courtesy of EOX, IT, GmbH. The viewfinder panoramas 3 arcsecond DEM, which is a global DEM, which has been created by British cartographer Jonathan De Ferranti. Of course, OpenStreetMap, originally by OpenStreetMap contributors, but we're going to use the Mapbox tile service kindly provided by Qualcomm Technologies GmbH. And also a special data set called the Ultras, which is a list of so-called ultra-prominent peaks, a database of those peaks that have topographic prominence higher than 1,500 meters. And that's the only data set which is not a public domain, though you can use it pretty much freely, but there are some restrictions on its use. Now, in terms of intellectual hierarchy, we are going to rely on topographic prominence. This is an extremely powerful concept. Just let me go over it very briefly. Topographic prominence of a particular mountain is the lowest contour line encircling that mountain, but no other point of higher elevation. Or to put it another way, it's basically the relative height that you need to descend in order to reach higher ground. It's one of the most reliable measures of the importance of the mountain. Mountains of higher prominence are usually going to be more important and more represented in traditional cartography than the mountains of lower prominence. As a prerequisite, we're going to need a VTS backend, which on a major Linux distro is pretty easy to install. And in the first step, we're going to create the base map. While creating base map, the first step that we do is that we add the global viewfinder panoramas DEM to a VTS storage. This is actually done with this one simple command, and the reason is that the global viewfinder panoramas are provided as a public resource by VTS resource by Melon Technologies. You could do the whole thing self-hosted, but it would involve lots of effort, which you might not want to do, so you can just use the public resource. Then we create a VTS storage view, which is pretty much a very simple JSON file. And in this JSON file, we say that there's going to be just one tile set that we just added. That's the viewfinder panoramas. And that we're going to drape over it an order photo, which is another public VTS resource. And that's that Sentinel-2 cloudless mosaic that I was mentioning earlier in the talk. So this is pretty much all we need to do to have a function in basemap, and then we can just point the browser to our server and to the server where we did all these commands and take a look at what's there. And what's there is actually this. So yeah, it's a global, not a map because there's no labels, but it's a global model of Earth, which is based on Sentinel imagery and on that global 90-meter dam. Pretty fun thing, considering that we just needed one JSON file and one simple command to create it, to have it on our server. But we're aiming, of course, to something more interesting than this. It's actually even searchable, you know, so we're looking at the area around Mount Rainier in the Pacific Northwest to see how far we're getting with this case study. Yeah, so there's Rainier, no labels, you know, we cannot really tell where we are. So the next thing that we do is that we start working those ultra-prominent peaks in, and we download the data set, and after we download it, The next thing that we do is that we create a thing which is called a geodata free layer. Now, this is another JSON file, and in the JSON file we provide a couple of information, like we name it, we provide an ID, and we say which data set is going to be used, and that's pretty much it. The next thing that we need to do is that we provide a style sheet for that particular layer, because the geodata is stylable in VDS, and in order to obtain some sort of a meaningful output from it, we need to provide a style. So we create a style, and in this style we just say that the labels are going to be uppercase, that they're going to have the name and elevation of the mountain, that they're going to be 19 points in size, and that they're going to be white. That sounds all pretty well. We add the layer to the storage view, which we used previously. And then we just take a look at what we've created. And yeah, it looks like this, actually. So we're not really getting what we probably wanted to get in the first place, because the labels are all occluded. And the reason why they're occluded is that there is no hierarchy rules which actually allow us to tell which of the labels are more important. There's about 1,500 ultra-prominent peaks on the face of the Earth, which seems like a fairly low number, but when you look on the globe, it actually gets pretty confusing. So what we do is that we solve the occlusions by the rule of higher prominence. That's the important thing here. We say that if two labels occupy the same space, we're going to display the label which has a higher topographic prominence. And in this way, we get no occlusions, and hopefully, we get a meaningful map. So we do this by just adding these two lines into the style sheet for the data set that we downloaded, and suddenly it looks a lot nicer, actually. What we have here is a map which makes a lot more sense. Like even if you take a look at errors from way away, we can see that we actually see the most prominent and most interesting features. We can see like Aconcagua, which is the highest mountain on the South American continent. The most important peaks in North America. Same works. Mont Blanc in Europe. Looks good, but still the map doesn't have too much information. There's only 1,500 peaks. So we bring in the main data source, which is the OSM, which is the OpenStreetMap database. And the OpenStreetMap database holds in it about 90,000 peaks with known prominence. So that's going to give us a lot more data to work with. We add the OSM-based geodata layer to the storage view. We're still working with the same file here, and this is another public VDS resource, so it's actually fairly easy to do. There's one thing that's remaining. We need to define a style sheet, which is being referred to here. Now this is probably too small for you to read, but we actually do the same thing here as we did for the ultras, which means that we solve occlusions by the rule of prominence. We do not want to have any occlusions, and we want the more prominent data to take precedence over the less prominent data. And once we do this, we suddenly get a lot more data. The resolution of the equipment here might not be real visible, but what you see here is that suddenly Rainier comes alive with all these surrounding peaks, and you get through a pretty impressive demonstration of the surrounding countryside. So this is good, but there is still a finishing touch that we should apply to be true to the principles of cartography, and that's the visual hierarchy. If you remember, what I was saying at the first part of the talk, talking about intellectual and visual hierarchies, basically the intellectual hierarchy of the map is a concept of some features being more important than others, and the corresponding visual hierarchy basically means that the visual style of the features should reflect on their intellectual hierarchy. Things that are more important should be more vivid on your map, while the things that are less important do not, the least important things should not be there at all because they would just occlude your map or clutter it. And the things that are less important should be less visually present than the more important things. So, but we are using just one size of the labels and just one color. So we're going to change this, and we're going to come back to the style. And what we do here first is that we go to the ultra-prominent peaks, which are the most important on our map, and we're going to say that we're going to display all of these in capital letters and in the highest, in the biggest size of the font. This is basically what this does. Yeah, the size is actually 19. It's outside that yellow box, but this is what this file does. And then we add these rather complex visual hierarchy styles to the OSM data. And what we do here is that we establish this thing called peak rank using the styling functions. And what we do here is that we actually say that we're going to divide the peaks into 5 ranks depending on their prominence, starting with the ultra-prominent peaks all the way to the peaks for which the prominence is not established, or peaks which might not be even local minimum. And we're going to assign through the style these ranks to them. And now, once we have those ranks, what we do is that we interpolate the color that we use for the labels from a saturated color to the least saturated color, gray or white in this case. This is a trick which is commonly used in cartography. The things of a higher that stand higher in intellectual hierarchy have more vivid saturated colors than things that stand lower. Okay, hopefully it's going to stay there. I'm going to get a live demonstration, so that would be a big pity. Anyway, so yeah, so this is the so in this way we interpolate the color, and we also interpolate the size. You know, if you take a look at the third line of what's in the yellow box there, you see that for rank 0, which is the ultra prominent peaks, we use size 19, and we go all the way to font size 14 points for the least prominent peaks. And what happens in the end is that suddenly our map starts to make even a lot more cartographic sense. If you take a look at Mount Rainier, hopefully I can show it in the live demonstration afterwards, where you will see it a little more accurately. And you see that actually we are using different font sizes and different saturations, and you can pretty much get the feeling of what's important in your map and what isn't. And this is what a good cartography map should do for you. So this is pretty much it. You can see the live demo of the map that we created here, hopefully at a lot better resolution on the address, so you can just take a look there. And also I'm providing links to other sources of BDS information. I believe that we still have a minute before the questions or something like that. Yeah, okay, good, that's fine. So I can do the live demonstration. This is actually the site I was pointing you to, so we can all point your browsers there if you have connectivity. Now, I have no clue what those black monsters out there are. Oh yeah, there they are. Okay, but we're not going to mind them. So we're in Europe, so I'm going to take a look at the Wetterstein mountain range, which is one of my favorite playgrounds in Europe, actually. And yeah, so here you see how it actually works nicely. I don't really know if you're familiar with the area, but this is the way it should be. These are the most important mountains in that mountain range, and the more important mountains are immediately better visible than the less important. So, and you know, this is not just a simple rendering. You can just browse around, you know, and you can see that the hysteresis rules in VDS are always going to give you an interesting view, and you know, in the end you can just take a look at the entire continent and it just all makes sense. So this is what we've just created. You know, another example is when I was showing you that viewing platforms, you know, that I actually looked up that place where that image was taken in New Hampshire and in America, and tried to create a similar view as the one that was shown on that viewing platform, and it actually looks very similar, which is, to me, kind of testifies to the quality of the design we've created. So, yeah, I think that's it. I'm going to leave the floor open to questions now.
Okay, I'm opening now the floor for questions. I may have to repeat the questions because so it's loud and clear for the video. So, who wants to do the first question? Okay, no one? Okay, so, oh, yeah.
If I want to print, how does it work?
So,
Because I'm doing the parallel with the orientation table. You were telling us that one of the application.
Yeah.
So I'm wondering about thinking about printing it.
Yeah.
Like it, but on paper and not only interactive. I'm in the mountain. I don't want. I do not always have a good network or something.
Okay, sure. The question was if we want to print it, how do we do it? Well, that shouldn't be too difficult. Like we just need a good monitor to start with to get a high resolution rendering, and then we just can screen capture it and print it. And like normally, like you would do a very high resolution rendering with our C++ library, but that C++ library currently does not have a label rendering yet, you know, so you need to wait a bit for it. But you can render it in your browser and just print it out, and it's going to look good. It's going to look good. But still, I believe that the main appeal of this is that the 3D map is interactive, that it's going to give you arbitrary viewing angles. So what you get is going to be nice, but I believe that actually using this interactively is even more useful.
okay, another question. Still have time for another one. I have a question. Is the code in GitHub or in a repository? I saw there.
If it's in on GitHub on the repository, that's the.
No, because I saw their GitHub link. That's for only documentation, but also for code.
Oh, there's everything. There's everything.
Okay.
Like the entire VTS 3D geospatial software stack is open source, so we're going to find everything: the streaming servers, the rendering libraries, and the command line tools. So everything is open source, and everything is on GitHub.
Okay, so if there's no more questions, I'll pass to the next person, Ladislav Horky. Sorry. Meanwhile, I would like to make an announcement. It's like we have business to business in the Posada da Juventude at 6:30. So if you register for the B&B, don't forget, and also you need to be registered by now. Second, there's going to be a free tour to Guimarães that's probably going to start here after the session's finished. So if you are interested in this tour, please talk with us in the reception for more information, okay? Thank you.